Everybody had a lot of questions about how I did the Linus Tech Tips data recovery. Well, spoiler alert, it wasn't super crazy, but there were parts of it that were super crazy. Parts of it that were so crazy that I felt like that I wanted somebody to at least check my work, check what I'm doing, because I was seeing insane stuff. Enter Allan Jude from Klara Systems. If you look on GitHub and you look at the work being done, Allan's doing the work. Welcome.
Hi, thanks for having me.
Allan and his team and everybody else and so on and so forth. But it's a lot of fun. So I figured we could talk about the recovery and, you know, what I did in the bowels of the recovery and sort of the state of things when I started, because it was an imperfect starting position and there were a couple of missteps along the way. But also to talk about ZFS in general. And, you know, if you find yourself in this situation, you've already messed up before now, but it's pretty good news for Linus, because even though this is, you know, months and months later, the reason it's months and months later is because Linus sort of let me play with his pool in this messed up state, even though we already got most of the data back months ago. There's always more data to get back, but, you know, as you sort of figure out each new dimension of how it's broken, you know, sort of have to solve the puzzle, and then you have to build machinery to automate over the data set to fix the puzzle in an automated kind of a way. So it's sort of a two-step problem. And I thought it would be interesting to talk about ZFS internals a little bit and the tools for recovery and that sort of thing, because ZDB is hugely more useful now than the last time I had to do this. And so that's nice. That's been really good. And if you're in this situation, using ZDB is really good because it's outside the kernel. If you're hacking on the ZDB driver in the kernel and you get something wrong and the kernel crashes, then you got to deal with a reboot or worse. And when you're using ZDB, it can just sort of read everything directly. And if it crashes, oops, that was a user land thing. Not a big deal. You can still do recovery.
Yeah, ZFS basically, ZDB compiles all of the ZFS code as a user space program so that if it crashes, you crash the program like a desktop application rather than crashing the whole computer. And ZDB has a bunch of flags where you could say, you know, these types of things where normally ZFS would stop your system dead because something's really wrong and it doesn't want to corrupt all your data. Because ZDB is mostly read-only as well, you can say, when you run into these errors, don't crash, keep going, maybe I can get something useful still. And it becomes safe because you're doing it all in user land and not with the, you know, the kernel driver, and you're not going to be writing to the pool. You're just kind of groping around on disk and finding what's there and seeing what you can make out of it.
Yeah, and that was hugely useful just because things were so broken. The geometry of the setup was a whole bunch of drives in groups of RAID Z2, so a whole bunch of VDEVs and a whole bunch of RAID Z2 VDEVs, but there hadn't really been any ZFS scrubs in years, so errors wouldn't be detected, and there were failing hard drives, which, you know, you'd expect after 4 or 5 years of continuous operation, which is actually pretty impressive. It's like, oh, this basically operated with zero maintenance for many years. On an ancient version of ZFS, I think it was like 0.6 point something.
Yeah.
And it's just, and backplane failure, which was introducing corruption in such a way that the more heavier loaded the disks were, the more it seemed to introduce corruption, which ZFS was catching, but then it started ejecting disks from, it's like, oh, this disk had a lot of I.O. errors. And it's like, well, that disk didn't really have a lot of I.O. errors. It just, the controller crapped out at that particular moment because the backplane crapped out because there was a lot of traffic across the backplane. And so all of those factors working in concert, along with drives that actually were dying, made the pool, you know, not importable at one point. So that was fun.
Yeah, or, you know, if it is imported and you start kicking out disks because of too many I/O errors, it won't kick out the last disk that would then switch to a faulted state. But suddenly you're missing a bunch of the other disks that might have been the bits you needed to be able to reconstruct a certain block.
Yes.
And so you don't want it to always be kicking things out. You know, under normal operations, you do want that because, you know, one slow disk can drag the whole VDEV down if it's constantly taking a long time to reply. But, you know, in a recovery situation, things are a lot different than in a, you know, production situation.
Oh, it was fun. We what we ended up doing was basically taking the whole pool offline and then stepping through each disk one at a time to just do basic diagnostics on each disk. And as we encountered a disk that had either an excessive number of bad sectors or IOs were taking a long time, we would just clone that disk to a new disk, just a literal block for block clone. And then we would remove that disk and set it aside. And that was sufficient to get the pool back into a state where it would import and things seemed like they were mostly working okay, without any sort of, other consternation to really have to worry about it. In doing that across a bunch of drives, there were actually 2 drives that had mechanical problems that did not finish their clone. And so it's like, well, that's 2 drives in 2 different VDEVs. I guess we could insert it and see if we're able to resilver. So we did that, and the resilvering was mostly successful, but the original 2 drives still had sectors on them that would have been useful in the recovery, because there were a couple of instances where other failures meant that we couldn't reconstruct some of the missing stuff. And that's actually where we are now, is like some of the stuff that is still kind of unrecoverable is probably because we needed to surgically move, individual LBA sectors. It's like, the record size was 128K, so we're moving these in 128K sets at a time, but ZDB works well enough to give you, it's like, okay, here are the actual LBA blocks that you're going to need in these devices in order to do this. So it's like, okay, I can do DD, worst case scenario. Yep. You don't want to use DD, but you can use DD to just go and get that 128K and surgically put it in the exact same LBA numbers. So when the ZFS machinery comes along to look at it, you can figure it out. Because figuring it out from the programming side of ZFS is less fun than that.
Yeah, any RAID Z recovery, ZFS is like, well, I only have to check some of the whole block. So I know that this version I've constructed is wrong, but I don't know which of the children of the VDEV contributed to the error. So it basically tries every combination of ignoring one of them and then using the parity to try and find, a version that does match the checksum.
But sometimes none of them match.
Yes, and that's when you can run into problems. And especially, RAID Z 2 and 3, it gets to be a lot of combinations, so it takes a while to find the right one. And yeah, if depending what was wrong, there might be no version that actually matches. And that was one of the extensions we did for you for ZDB, was then just return your best guess instead of nothing. Like normally in ZFS, you would never do that, right? I give back the right data or I give nothing. But again, in a recovery scenario, it's like, if this is just 1 bit off or something in a video, the video is still going to be mostly usable.
Yeah. So what we mean is, like, you've got a 30 gigabyte video file and 128K is messed up inside the video file. You can just tell it to ignore that, and then ZFS will just not give you the entire 128K block. But sometimes we were getting corruption on things that contain references to directories, and it's like, well, let's try to do something with that anyway, because it would be nice to be able to recover the files. And so sometimes when the file is not recoverable from the directory view, you could still access the file by object number in a data set or by block number. And so you can just dump everything that you can get from your list of objects in a data set and be like, oh, there's my file. There's the specific file that I'm looking for. And you can cherry pick that out. We did that with a few files, but I never did build a tool to sort of automatically try to do that, because the ZFS recovery ignore the fact that this file doesn't match its checksum. If we turn that safety off and I still get a 30 gigabyte video file, who cares if it's got a little corruption in the middle of it?
Yeah, because normally ZFS would just stop reading at that point and be like, hey, that file's no access.
And then you lose 30 gigabytes of data, but it's...
Yeah, or everything after the corruption. You can read the first bit of the file, but then it's like, nope, that's corrupt. And in production, that's what you want. Yes. You never want bad data. But in recovery, you want to take some of those seatbelts off. And you were talking about the automation of that, and that's what led me originally to start working on ZDB at the OpenZFS Developer Summit Hackathon, I guess 2021. I'd seen people like writing Python scripts to drive ZDB, where they would print out the indirect blocks for a file and then iterate through those in Python and be like, all right, now read this LBA and put it over here and then try to reconstruct the file. I'm like, well, ZDB has all the bits. It's just somebody just didn't write, the loop over that code where you could just be like, here's a data set and an object number. Please extract it and write it over here. And so I built that, and it allowed you to recover a file and work nicely. But I had this issue when I was building it of, well, I don't have a pool that's corrupt in strange ways to test this on to make it be able to do the right thing when some block isn't readable.
You do now.
Yeah. And then, Wendell calls up and he's like, hey, I have this pool and it's broken and we can give access to it and we can try some of these tools. I'm like, that'll be perfect.
It has been really interesting to look at ZFS at point blank range, but also to attempt to do recovery in these kinds of situations. And like, again, to be clear, Linus already got all the stuff that he cared about back a long time ago. And so it's been sort of my desire to, do a little bit more forensics at a point blank range, because even though, even though we have some of these blocks and there's really minor corruption, because the backplane, I guess, introduced corruption, or because we lost a few bits here and there in the 128K, records, it was actually useful to do things like dump, 2 of the copies of the metadata that was supposed to be for a particular directory or indirect block list or whatever, and then compare them and say, okay, neither one of these will decompress, but theoretically these blocks should be the same. How do they differ? On what bits do they differ? And then let's just, if that's 1,000 possible combinations, let's just build a little script to try, all 1,000 possible combinations and see if we get one that will actually decompress correctly, because that might be an option. And then it's like, boom, we've unlocked a few more files. It's tedious and a huge pain, but those kinds of things are possible if you are really desperate or insane, as the case turns out.
Well, in this particular case, it was just such a good opportunity where this fairly rare but realistic failure mode happened, and we have access to the pool for enough time to actually do something other than just get the recovery and get it back online. And it made it, it really gave us this opportunity to help flesh out the tools that are available when something like this happens, so that, when it is a dire situation, that you're not having to build all your tools from scratch still.
Yeah, if it was a dire situation, about hour number 4, people are freaking out and breathing down your neck. And we did not have this in this scenario. So big thanks to Linus for that. But also just the curiosity of, okay, let's just see how deep the rabbit hole goes on this, and let's just figure this out. In terms of ZFS and ZFS internals, this could not have been a better failure mode. Like, looking at the post-mortem on this and looking at how we had, multiple drive failures, like physical drive failures in a pool, plus a backplane that the harder you push the backplane, the more corruption it introduces. If you're just doing light IO, which, is restricted by the network in a lot of cases, like I'm just going to copy files from here to there, you'd never see any corruption. But if you needed to do a scrub, that's sort of the first place where things started to go wrong. It's like, well, if you're not 100% sure about your hardware, don't scrub, because that led to some problems.
Well, or, ZFS reacting maybe overly aggressively to an issue.
Yeah.
Kind of getting back to what you said earlier, the first thing is, if you're in a situation where things are getting corrupted and so on, stop touching it. and if you can, work off, like you said, a clone of the disks, so that you have the originals and you can still send them away for, more forensic recovery or something. Now, that wasn't really an option in a 1 petabyte pool situation.
Across multiple
clone
chassis,
every one of these, clone every one of these disks and just, have a spare petabyte laying around and do that. But to the degree you can, you want to avoid making changes to the pool. So sometimes that is even to the point of, when you're trying to do imports, make sure you're doing the import with the read-only flag on the pool, so that ZFS won't keep adding data, like writing stuff to the disks. And you just want to see, how much can I get back just read-only, and not changing things. And,
when I first got hands on the pool, they had tried some things, and it was necessary to roll back the transaction log kind of farther than ZFS wanted to, because it had already added some stuff to the transaction log that I felt like had moved us farther away from a working system. And so once everything was put together, it's like, all right, let's just unwind all that stuff that happened back to here. And that was a much more recoverable situation than what I started with.
Yeah, for sure. And that's one of the slightly interesting things about the way ZFS works with the transaction groups is because it was originally designed when disks were 512-byte sectors, it would have the last 128 transaction groups in the Uber block ring. But because disks have 4K sectors now, we only get 32. And looking at ways to maybe fix that just so that in the case where you do need to rewind, you can rewind a bit further. Or another idea that was proposed at a previous developer summit is, while we want to keep the last X transaction groups, maybe the tail end of that ring should have like a grandfather policy or something where we, keep only like the 1,000 transactions ago or something, so that, the last couple of things on the ring are varying degrees of much older, so that, if the last 30 transaction groups isn't enough to get you back for the problem, because depending on how busy the system is, you can go through your 30 transaction groups in a couple of minutes.
Yeah.
And, being able to at least step back half an hour might be a big difference between being able to import the pool and not.
That would have been handy here, yes.
Yeah. So looking at making sure that ring gets bigger at some point, using a couple of different mechanisms there, and maybe having some policy of, the very tail end of that ring, maybe we have some kind of age out system so that we do keep a couple of slightly older Uber blocks so that we can find where that metadata is.
Yeah. That kind of thing would definitely be super handy.
The main reason it doesn't do that right now is because it wants to make sure when it writes an Uber block, that's an atomic write, right?
Yeah.
We want to, always write a whole sector. And so we could do something that involved more of a like read, modify, write thing, but we'd want to stagger it so that, if we do have a shortened write, we were in the middle of writing an Uber block in the ring when the power went out or the system crashed or whatever, that the other Uber blocks we took out aren't the neighboring ones, right? We took out, every 31st or 32nd Uber block in that list, not a bunch in a row where now your best recovery chances all got blown up.
Oh, yeah. Yeah.
But I have noticed certain models of hard drives sometimes don't really like the way we do the Uber block ring. Especially spinning disks, we're writing to the same offset on the disk all the time, right? So the ZFS labels are like the first 512 and the last 512 bytes of the disk. And then in each of those 256K labels is a 128K Uber block ring. And so ZFS is writing that like at least every couple of seconds to that same spot on the disk constantly the whole time the pool's there. And I had a disk where the other side of that was an unused swap partition. And eventually those disks developed read errors in that unused swap partition, partly because I think those sectors had never been written ever. And then the ones beside them were getting written to constantly. And eventually it just, they never got refreshed or something. And they started, the smart test would be like, I can't read that sector anymore. And I thought that was kind of interesting to see, because spinning disks don't have something like wear leveling where they're going to replace the sector the same, like eventually they do if it fails. But it was interesting to see that, all the Uber block sectors work fine still because, they've been written to constantly and they were always busy. But sectors near that were never used were suddenly having issues.
Interesting. That is very, very interesting. Sounds like
I only saw it with one model. It could have been a firmware bug or just, because of how tight the sectors are together and those ones just never got written to. Whereas if, they'd actually gotten written to once a year or something, they might have been fine. I don't know.
You got to do the patrol read, rewrite constantly. But, now
Or
mechanical hard drives have a really surprisingly low write endurance lifetime. Like 20 terabyte drives are only rated to be rewritten about, what is it, like 100 times their entire lifetime?
I guess it depends. I think part of that is just trying to force you to buy the pro versions of the drive. I don't know. But yeah, so I did
version of the drive.
I suppose that's true. But yeah, I did think it was a little weird to see spinning a hard drive and it would be like, its rated workload is like 180 terabytes a year. I'm like, that seems low.
Yeah, I'm a little worried about that, but maybe it'll be okay. Also worried about the transfer rate of this too, because and one of the recovery tricks was just using ZFS send with all the safeties turned off, because then it's a lot easier to read from the data set, the copy of the data set that's been moved from A to B, because if you had errors in the first data set, well, it copies everything that it possibly can, but the copy of the data set is more recoverable, even if it's in the same pool, and you don't do that unless you're to a point where you're sure that that's not going to cause any other problems. But copying the data set, even in the same pool, that was a really interesting recovery situation as well, because the act of just moving the data set is like, oh, this is actually now more readable than it was before.
Right, because all the metadata is now correct. It's either correct or missing. It's not, there's some damaged stuff in here that I'm going to trip over.
Yeah.
And, it's on hard drives that aren't going to, spuriously return errors and so on. And so, yeah, it's kind of in, like you said, with the other ones, when you were cloning the drive, the same data, even if some of it's missing on a working drive, is always more usable than maybe slightly more of the data, but on a drive that's randomly timing out and taking a long time or returning errors.
Yeah, a couple of those, when looking at ZFS at the point blank range to try to, because I was trying to get metadata blocks that were identical, and a couple of times I would pull the 128K metadata block that was from a damaged drive, and the entire block was there except for 512 bytes in the middle that was just all zeros, and it's like, well, obviously the drive had a read error here, and but it made it really easy to spot in a hex editor, because there was a lot of information there, almost random, I guess, because of the compression.
Yeah. And then, if you have a second copy from a different drive and it has a different hole in it, maybe you can stitch them together.
Yeah, that's where we ended up. Don't be like that. Do your backups, do your scrubs, do your stuff.
Actually replace the failed disks when they fail instead of just leaving them there to rot in the back server room forever.
Have some spares, just a few. That was another thing too, is the chassis were all completely full. And so it's like, okay, I would like to not remove the failing disk. This is actually, would you agree? Because I always tell people, don't take the disk.
Yeah, well, always make sure you have a little bit of slack in your chassis, because, when a disk is dodgy, what you really want to do is an online replacement.
Yes.
So you're doing zpool replace, but you have the old disk still working while the new disk is getting a copy of it. Because especially in the case where if you have multiple disks failing, this way you're still maybe getting to be able to read from the drive you're in the process of removing until you have a perfect copy of it. It doesn't get removed, and it just lowers the chance that another drive conking out is going to cause your pool to get suspended or faulted.
This is incredibly sage advice, everybody. You should definitely listen to this, because it is very hard-won advice, very good advice. It's like, don't pull the disc.
Yeah, I would say you probably also want some cold spares or something. Like, if you're buying a system and you're building with lots of hard drives, order a couple more drives than you need, so that when it's time to do a replacement, you have some spare. Because as we've seen with supply shortages and so on, it can be really hard to get the disks that you need in a hurry. And, those disks might not, that model might not be available anymore. And while, ZFS will tolerate you using different replacements or whatever, just order a couple more disks than you need and have them laying around is really helpful. And leave some slack in your chassis, because it might also come up, like with another pool we were having somebody design. In the future, we might want to stick some SSDs in here for metadata VDEVs.
Oh, yeah.
And so having a couple of spare slots, we can always add more hard drives later if we end up needing the space and we don't use it for SSDs. But you can't remove a RAID Z once it's in there. So maybe don't fill up every single slot in your chassis as part of the pool, and leave yourself a little room for who knows what's going to happen down the road.
That's also another piece of advice that I kind of wanted to get into. Well, the metadata special device, I love that. I run that myself, but more importantly, metadata copies equal 2. It's not a default. It probably should be at this point.
Well, so most metadata is copies equals 2 automatically. And the pool level stuff, like the stuff about data sets, is copies equals 3.
Okay.
Or actually it's copies plus 1 and copies plus 2.
Okay.
So if you set copies equals 2, then any data that's normally stored twice would actually be stored 3 times. Because it does the base plus the extra copies for the metadata. but yeah, you can't control the metadata only copies separately. But there is the dataset setting that goes the other way, which you probably don't want to use for this stuff, which is redundant data equals most versus all. And that specifically for those indirect blocks, the blocks that just point to more blocks, above a certain level, it will write fewer copies of those. And that's specifically designed for databases where, you're making like an 8K change and you don't want to have to write 4 levels of metadata multiple times, so you can reduce it. But most of the times you don't want that, other than, there's a special case of this is a database and we're backing it up differently and so on. But yeah, you definitely want to be careful with your metadata. And that leads to the question about those metadata special VDEV devices. You definitely want mirrors for that. And I usually suggest at least 3-way. And then I try to make it not all 3 the same SSD, because it's a mirror. You're going to write all the data to all the SSDs the same all the time. And so that means they're all going to wear out at the same time. And that's not good. And so, yeah, you probably want a 3-way mirror, and at least one of those SSDs should be a different model or a different brand or something that's hopefully not going to wear out at the same time.
Because that could happen. There are firmware bugs. Let's not forget the 65,000 hours of power on and then it powers off.
Yeah. I recently saw one where a mirror of like Samsung 970 or 870 Evo SSDs in somebody's home media pool, both SSDs started having read errors. Luckily not in the same sectors, but both of them were basically dying at the same time. And we actually did the same thing of basically cloning those to 2 different SSDs and replacing them, and that stopped the pool from keep suspending itself, because it was like too many read errors from that SSD kicking out of the pool, and then too many errors from the other SSD, and now we have no metadata.
I have a striped mirror in my system, in one of my systems, of 2 terabyte SSDs, and there's one spare 2 terabyte SSD. So it's like as soon as you start seeing errors in those SSDs, use this. Yeah. But they were all staggered. I didn't have the luxury of using different brands, but they had different levels of wear on them when I started. So
exactly, that's basically the other option is, add the 3rd one after a couple of months or something, so that it's not at the same wear point.
And that's also really hard one and advice. Just do this tiny little thing, and future you will look back and thank past you for having done that.
After a year, maybe replace one of the SSDs preemptively.
Just for fun.
And then you can keep the old one as a spare and swap it in later, because it has some endurance left on it. But or set up some monitoring with Smart and watch the endurance on those. Because when it's getting low, you're going to want to preemptively replace at least one of the 2 in time. And I've seen the same thing. People build a pool with a Slog on a relatively cheap SSD and then wear out its entire endurance. And then suddenly it goes read-only. And ZFS is like, well, a read-only Slog isn't very helpful.
Yeah.
And then it's like, yeah, you should do something about that. And, that might involve just removing the Slog temporarily and not losing all that performance benefit. But, the system's not very happy when your Slog wears out.
Well, I think I'm trying to think if was there anything else that you can think of that was interesting about the recovery? In the end, we got, by percentages, it was like 99.8 or 99.9% of the data back. And we probably could get the rest of it. It's just tedious LBA block surgery, and Linus doesn't care at this point. But we have some time, and we have some stuff that we can do that maybe is a wider benefit to the community for CFS recovery. But I was trying to think if there was anything else interesting about the recovery.
Yeah, I think mostly looking at the features we would add to ZDB based on it. We have the improved version of my recovery mode for individual objects. We have the return the data even if the checksum's wrong, and looking at expanding that to let you selectively try or iteratively try each of the RAID Z reconstructions to see which one looks most likely to have been the right one. And making sure that that's accessible.
I want a tool that will give me all of the metadata blocks, and I can compare them and see, okay, here's how this was, and here's how this was, and here's how this was. Although I never did find a pattern in the way that the backplane was failing, just that the the checksums that were, because one of the thoughts that went through my head was if the backplane was failing in such a way that like this packet of data that's in flight was coming from bad RAM or something, then these 2 bits are always bad, or these 3 bits are always bad. But that seemed not to be the case.
Yeah, it sounded like maybe they were just all zeros.
Yeah, a lot of the time.
Which says maybe it was more of a problem at the transport layer, probably like electrically or something, and it just went bad or couldn't ECC it or something.
Yeah, there is supposed to be in-flight data with that. That's another dimension of this. So these were all SATA disks into a SAS controller. SATA actually operates, I mean, if you really like get super into the weeds here, SATA operates at a lower voltage, lower differential voltage, and is less noise immune than SAS signaling on the same cabling. A lot of people are like, oh, it's the same cabling. And it's like, well, one, SAS has a redundant path, but the redundant path is handled at a protocol level. So you can choose that path in the driver, or the controller and the driver can agree, oh, something went wrong on this path, let's try this other path. None of those are options with SATA. And the other thing is that at an electrical level, the characteristics of the differential signal with SAS is better than SATA in general, and will push a signal over a longer distance. So,
yeah. But, it's definitely an interesting case to investigate just because it was, one of these real world failure scenarios, not a theoretical one. And we had enough time to be able to dig into it.
Yeah. And without a lot of headache, basically, I would say probably 90% of it was available immediately. Just, okay, let's take a deep breath, assess where we are, look at what's happened. Okay, this is our plan of attack. And, Jake was helping me with the recovery. I was doing it all remotely. And so it's like, okay, swap this disk, move this cable over here, swap this disk, move this cable over there. And honestly, probably spent more time just waiting on him to have time to do that than, okay, this is good. And then finally it was like, wait, this chassis is also bad. And it's like, what have you done? No. So it's like, okay. And then we moved everything over to the new chassis, and that's where it's been for the last few months. And so things have gone a lot better there. But, immediately, the machinery of ZFS, once you've taken the faulty hardware out of the equation, the machinery of ZFS, basically out of the box, 90% recovery of a petabyte. That's pretty good.
Yeah.
And that it's the correct data because of all of the integrity stuff. In any other scenario, you wouldn't know if what you got back was what you had actually written.
Exactly. Yeah. Just even thinking about basic hardware RAID of mirrors that your BIOS can do, or a real controller or whatever, is it tries to write the data the same to both disks. If at any point for some reason one of the disks isn't the same as the other, it wouldn't know which one of those 2 blocks is right. Wouldn't know they were different most of the time either. So it can do its patrol scrub thing where it will just rewrite the second disk to match the first disk to eliminate the problem. But when it's doing that, it doesn't know if the first disk actually had the right data or the wrong data. Whereas ZFS, because of the checksum, it knows which one was wrong and fixes the other ones.
I've done videos on that, demonstrating that with different controllers. And then I get these long missives from these graybeards, I guess, that work in this. And it's like, no, that's not how it is at all. I have this fancy whatever, and then they have the model, and it's like, it knows when and it can check and it's like, no, well, if it's doing that, it has an extra record. It's using 520 byte sectors instead of 512 byte sectors, or it's doing an extra write somewhere or something, and they're like, no, it's not. It's like, here's in the manual where it says you have to use 520 byte disks with this solution in order to get this feature, and then I never hear from them
in order
again.
to fit that checksum, and that checksum is a lot smaller than the one in ZFS.
Yes.
Right, the ZFS is using a 256-bit checksum. That's not going to fit in that extra little sector. And
then people are going to pop up and say, oh, 8 bytes is fine. And then at that point, you're just arguing math. You're arguing 2 plus 2 is equal to 3, and that you've lost. So give up.
Yeah, it's like 64-bit checksums. We stopped using those how long ago because of collisions?
Certainly, there would have been a lot of collisions here. I mean, that's kind of what's happened. It's like, okay, I've got a couple of candidate copies of this, but nothing will actually at the wire level. Even there were enough checksum collisions that data with errors was getting through. Is what I'm saying, and we can demonstrate that was happening. Looking at the post-mortem of this, but constructing that argument is 100 hours in to a recovery like this, because then you've got everything laid out and you can see, well, the only way this would get through that layer is if it passed the checksums of the physical layer. Like SATA has
the physical layer, it's just like ECC though, so it can fix 1-bit errors and detect 2-bit errors, and then after that it's like throws up its hands.
Yeah, well, you're not, after a 2-bit error, you're not guaranteed to even detect it, which is demonstrably what happened here, because we were otherwise getting errors, and it's like, oh, let's retry this. But consumer hardware, a lot of the time, when you get that 2-bit error, a lot of the time it'll just silently retry. A lot of systems are configured, even at the PCIe level, on consumer systems, PCIe address error report, or PCIe error reporting is not turned off, but it doesn't report to the system because people were freaking out and saying, why is this?
Well, yeah. In particular, especially like Windows 95, Windows 98, if the hard drive ever returned an error, Windows was like, your drive's toast, and it would scare people. And so hard drive manufacturers made the drive like, well, we'll retry 5 times internally before we ever return an error up to the controller, that maybe, the driver and the OS will try 5 times again. So now we have 25 tries before we finally get an error. And that's where we, ended up with these drives with, time limited error recovery, where it's like, please don't just go away for 90 seconds retrying and just give me the error.
There's still a lot of drives that do that.
Yep.
Consumer drives.
Yeah. And talking about the other bit you talked about, where ZFS was kicking drives out because of these errors that it turned out were the backplane, not the disks. We just opened a pull request last week to make ZED, the Linux ZFS event daemon, more programmable, to say, you need to have this many errors in this many seconds before we kick a drive out, and be able to control that with the new Vita properties mechanism.
Oh yeah, it'll be nice to use some userland scripts to tie that together with Smart, and it's like, okay, let's do a quick online Smart test on this drive that has errors, because that's what I did in a lot of the case for Linus's setup. Was, okay, this drive is producing a lot of errors that seem like they're read errors, but let's actually take the pool offline, shut everything down, and then let this disk run with a long offline Smart test. And so we just leave the disk alone for a while, let it do its thing, and if it comes back clean, it's like, I think this is a cabling backplane issue with this particular drive.
Yeah,
not always. There's no guarantee of that, but
yeah, if the drive didn't think anything was wrong, then maybe move it to the other chassis and look, it works fine. But if the drive is like, I got corrupt sectors all over the place, then it's like, well, even if the backplane's the problem here, that drive is also toast.
Yeah. And that's what we had. Fun times. But step by step, I guess, what would your advice be to somebody in this situation? Probably hire your company to deal with it.
Yeah, well, I think the first one is like, if you can, shut it off and stop poking at it. And if it's practical, work off a copy of all the data, like image all the drives and work off that. Not always possible, because if you're talking about hundreds of terabytes or more, that gets kind of impractical. But if it's a smaller pool and that's an option, make sure that you don't take any of your future recovery options off of the table. Yeah, by having modified it too much.
Work on the copies of the drive. ZFS does not care. It's like, oh, my worldwide number is different. ZFS does not care.
Nope. ZFS has its own worldwide number written on the label on the disk in 4 places. And if you clone the drive, that'll be the same, and it won't even know. Yeah, so if you can, stop touching it. If you are going to touch it, work off a copy if you can. And then, call for help, because we might be able to sort you out really quickly without a lot of headache. But if you keep poking at things, the longer it's been since the problem, the less likely we'll be able to rewind to a point before the problem.
I think when we started one, it was like, this has been scrubbing for a week and it doesn't look like it's ever going to finish. And it was just like, oh no. It's like, the pool's already read-only. What have you done?
Well, if it's read-only, the scrub wouldn't make anything worse, unless the load just happened to make a hard drive mechanically fail. But
it went read-only as a result of the scrub.
Okay.
That's not an ideal situation.
No.
Let's see, what else is interesting. What else is, if you find yourself in this situation? ZFS send, actually, this is also like kind of a branch. ZFS send as a mechanism for doing backups even if you have an absurdly huge data set like a petabyte, and even if you're adding gigabytes of video per day, ZFS send is still the least insane way to deal with that, because it's a journal. It's just, it knows what changed from yesterday to today. You don't, there's no cost to look that up. You can just start sending the data.
Yeah, every block has a birth time of which transaction this block was changed or modified at. And so when you say, give me everything that changed since this snapshot, it's just can start sending it as fast as your disks or network can go right away. Whereas rsync has to like look at every file and be like, when were you last modified? Okay, let me read you and see what your checksum is. Well, I'm also doing it on the other side to see if it's changed. Yeah. And it's like, wow, that's going to take forever. And so, yeah, in a previous attempt doing a recovery, they were trying to use rsync to do the recovery so that it would skip over the files that would have read errors. But it was going so slow, it was going to take them weeks and weeks to get this data copied off to another machine. Whereas when we switched to ZFS send with the extra settings we added, we made more tunables for ZFS send so that when it encounters corruption, it can just return a known string of, this was a ZFS bad block. That feature's been around for a while, but if it encountered a specific object you couldn't read, it would stop. Any corrupt metadata would make it break down. And we made a switch. You can say, no, keep going no matter what kind of thing. And they were able to get most of their data copied over to the other machine in a couple of days instead of a couple of weeks. And that was mostly just down to they only had 10 gigabit network.
I would also say that ZFS send also affords really interesting recovery possibilities in that even if you had an ancient copy of the data set and the object, and you hadn't backed up in weeks, in this scenario where we just need a few 128K blocks, as a matter of chances, there's a good chance that one of those blocks exists on the old system, and we could pull it off the old system and put it on the new system. And it's like, oh, this data hadn't really changed in a while. And it's like, oh, well, actually a bunch of files in this folder did actually change. And it's like, okay, that would all be updated. But we could still pull the files and pull whatever blocks we needed from the old data set. And we would know because it's stored the same way on the remote data set as it is the local.
Yeah, and actually, a feature for that got committed to ZFS 2 or 3 weeks ago. It's called like a repair send. So if on your backup copy, you end up with data corruption of a specific sector, or it could be your master copy, one of the two copies goes bad, it can construct the right send thing to just send the data that you're missing from the backup back to the primary, or from the primary to fix the backup, where you can say, this snapshot, this block is broken, just send me that bit. And you can actually repair broken data from your backup without having to do a full restore or manually try to do this, especially if it's, in a not the live version of the data.
That's amazing.
Yeah. So repair send got committed to OpenZFS master, I think 2 or 3 weeks ago.
I'm thinking about repair send and those metadata special devices as an extra way to hedge your bets. That sounds really exciting.
Well, just remember the metadata special devices are not an extra copy of the metadata. They are the only copy. So redundancy out the wazoo on those metadata devices.
We'll send those offsite in real time. I don't really worry about the data, but it's like, let's send the metadata devices offsite in real time. Just in case. It's like, oh, we don't have those blocks. Well, that's okay. We'll get those back eventually. So with Linus's recovery basically out of the way, let's look to the future. What's on the horizon for ZFS that you're excited about? What's coming down the pike?
I think the biggest one I'm excited about is the block reference tree, or BRT, which is basically per file cloning, and also allows you to say, move a file from one data set to another without having to copy all the data.
Ooh, that's nice.
So it's basically a kind of opt-in better version of dedupe. Is the way it kind of works is you can specifically clone the blocks of an object and write it to a different data set or the same data set in a way where you only have to write the metadata, and it keeps it in a much more efficient tree than the dedupe one. And so, it'll basically let you easily clone a whole file. So if you have like a VMDK image or something, you can just clone the whole thing really quickly without having to clone the whole file system like you do now. Where currently I suggest people, make a separate data set for each VM so you can easily clone it. But being able to do that on a per file basis is really interesting. But also just being able to copy a file to a different data set without having to actually copy all the data when it's big. Or specifically, if you're trying to restore a copy of a file from a snapshot, currently you end up making a whole new copy of it rather than actually referencing the blocks you're keeping around for the snapshot anyway. And so the block reference tree allows you to do that and would hook up to, the CP reflink thing in Linux, or a similar thing in FreeBSD, where you'd be able to just easily clone a file. And it's much faster because all you're doing is writing out the indirect blocks, the metadata for the file, and pointing to the same blocks on disk. And it goes in this block reference tree where it keeps track of, hey, if you delete one of the copies of the file, we know we can't free that space because it's still in use by this other copy.
Nice. That does sound like an amazing feature that I would use the heck out of a lot.
Yeah. And that was developed by my friend Pavel Dodek, who did the original port of ZFS to FreeBSD back, I don't know, it's got to be almost 15 years ago now.
A lot of enterprises are going to benefit from that feature.
Yeah. And, is one of the only things that ButterFS has that ZFS doesn't. So
I'm not
other than lots of bugs.
Yeah, there you go. Yeah, I wasn't gonna say it, but there we go. It's and then also NVMe. So I'm always all about ZFS on NVMe, and I wanted to go really fast. But in the past, when I've used it, it makes an insane number of memory copies. But you have a talk coming up, and I will link to that in the description when it goes live. Which this video will probably come out after you've given the talk, but we're recording it before, so you should you can plug your talk a little bit, and there'll be a link for it in the description.
Yeah, so not quite got to solving the mem copies as the problem, but because of the way ZFS was built and the fact that it was designed in the year 2001, and nobody had, Flash wasn't quite really that big of a thing yet. And then when it was, we're gonna have these tiny flash disks that we can use a little bit of to accelerate the pool with like Slog or L2 Arc, not I'm going to build my entire pool out of this flash that would have cost way too much money at the time. And so ZFS does a lot of things to try to optimize for the fact that the limitations of hard drives, right? That your average seek time is going to be like 4 milliseconds or more. Like 4 milliseconds is low for a hard drive, basically. Whereas for an NVMe, your read and write latencies can be less than 100 microseconds. So it's 4,000 microseconds is the best a hard drive can do, and the NVMe's can maybe do it in 50.
Or 16
versus 50. Yeah, or 16. Yeah. We're getting close to the day where we're going to have single digit microseconds for these things. And the other big thing is the interface. NVMe, so with SATA and so on, you can queue up a bunch of commands, but really the hard drive's doing one at a time, right? It can only move the head to one place, do some work, and then move to another place. By queuing commands, you can help it decide which order to do them in and some stuff like that, but that's the limitation. And SAS is the same thing. With NVMe, you have a bunch of different queues, each which can contain a bunch of different commands. And so, even on your typical drive, you have like 63 queues plus one for admin commands, so they never have to wait. And then a depth of between like 16 and 64 for how many things you can put in that. And so to get the performance out of an NVMe, ZFS needs to actually fill those queues and give the NVMe lots of work to do. But because it was kind of designed for hard drives, ZFS is like, I don't want any of the queues to get too long because it might take too long. Like we don't want, if something important comes up, we don't want it to end up at the back of a really long line. But with an NVMe, that's really not going to happen. And so you have to teach it these things. And so in my talk, I talk about some of those changes and what we did to ZFS with some patches to get it to go faster. And for the customer we did the work on, they had a NVMe over Fabric pool, and we got it from going, 2 and a bit gigabytes a second to, like 7 gigabytes a second.
Nice.
Which made a big difference. And the big thing was getting the latency of the writes from like 25 milliseconds down to like 13.
Oh yeah, that's a big improvement. That's 100.
Yeah, and there's still more work to do to make ZFS better at it, but it's just ZFS needs to learn how different an NVMe is than a hard drive.
Eventually, it's just going to be persistent memory.
Yeah, and that's the whole other thing. Another OpenZFS developer did his thesis on persistent memory and has some designs on how you'd make the slog work better on persistent memory than the current way it's set up to work on like an SSD.
Nice. Well, thank you for joining me. I really appreciate it. It's been an interesting look and not super technical. You can kind of understand what we did at a technical level to recover Linus's pool, but the lesson here is definitely an ounce of prevention is worth a pound of cure. Check your backups, monitor things, pay somebody to monitor your stuff, whatever the solution is. But it was not a completely catastrophic situation, even given less than ideal inputs.
ZFS will try very hard to make sure that you don't lose your data in spite of whatever you're doing to get in its way.
Yeah, the more experiences I have like this with ZFS, the more I'm convinced that there's really no other option if you care about your data, because I've worked on other things, and I've worked on those fabulously expensive enterprise systems, and even those companies don't care that much about what it's like. Oh, you should have bought our other thing that backs up your stuff off site, and because you didn't, this is your punishment. It's like, well, thanks, large company that we paid millions of dollars. Definitely, if you need somebody to babysit the pool, Klara Systems is they're available. Don't pull me into something that's going to take hundreds of hours and melt my brain, because oh boy. But you can do it with them.
Don't be like Linus and just ignore your pool. If you don't want to manage it and maintain it, you can hire Klara to come in and check on it all the time and send you a report every month saying, this is how it's going, this is what you need to do, this is when you're going to run out of space at this rate, and somebody needs to watch the pool. It doesn't have to be you, but somebody needs to watch it. Otherwise, you end up in this situation.
You got to keep an eye on things. Yes, I would wholeheartedly agree with that. Klara Systems, Allan Jude, thank you.
Thank you.
And we'll see you later. I'll be in the forums. You'll be, you can probably be reached for phone support, but you need a retainer for that.